There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, and protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromide, lithium, beryllium, and barium. Isn't that interesting? I hope you're all paying attention. There's going to be a short quiz later on. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, and zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Okay, everybody. I have a water bottle, and we're going to do a little experiment today. It's got 25 milliliters of water, and inside here, there's air. Now, inside this bottle, there's mostly air, but let's assume that the water is saturated with water vapor, which would be about 3% of an atmosphere, 0.03 atmospheres at room temperature. Now, what I'm going to do is I'm going to take this and put it in this microwave over here. And I'm going to take the cap off and microwave it so the water goes up to boiling. All right? So I'm going to microwave it for a minute. It's got 25 milliliters. Let me time it. Okay? We got 25 milliliters of water. The water's heating up. And as the water heats up, the vapor pressure of water increases, and when it gets to 100 degrees Celsius, it will actually be at 1 atmosphere, and all the air will be driven out. And I'm going to cap it. As soon as we reach a minute, I'm going to cap it, and we're going to see what happens. All right? We're going to see what happens to the bottle after we cap it. Okay, it's 43, 45 seconds. We're going to go up to 1 minute, 60 seconds. Now remember,
1 minute equals 60
the vapor pressure of water is going to go from 0.03 atmospheres to 1 atmosphere. All right, now I'm going to turn it off. Let's be careful. And I'm going to quickly put the cap on. It's very hot.
So 0.03
very hot.
1
and now I'm putting it here. And you can see what happens to the bottle. Very rapidly, it shrinks down. Now, what's happening is as the water cools,
yeah, what's happening?
The water vapor condenses, and that creates a vacuum, and the air pushes in to equalize the pressures. And you can see that we have a really flat bottle. Now you can, but it's very dangerous, you can actually heat the water up again and it will, with the cap on, it's a little dangerous. I don't advise doing that. But it will cause the thing to go up again.
But the question is, will you do it?
You know, this is softer. The bottom part is reinforced plastic so that it gets a little bit hard to compress. But the incredible shrinking bottle. Okay, in summary, you can use water in a bottle to cause a can to flatten to a pancake. Thank you. You can see it got bigger. Okay.
Now it's tall and skinny.
And now it's compressing again. Very cool. Very dangerous too, because scalding hot water is, as they say, scalding hot. And you don't want to touch it down here. It's really hot. So there's an example of chemistry in action. All right. Thank you.